Hi, I'm Ted Mansell, and in this talk we'll look at some new details on aerosol effects on lightning production, and specifically at what role enhanced condensation might have in promoting electrification. The main idea of convection invigoration by aerosols is that under the right circumstances, adding CCN can help release more convective energy. The mechanism is a delayed warm rain process that allows more liquid to be carried above the freezing level and thus provide extra latent heat of freezing. The effect depends on conditions, of course. And an invigoration effect has been inferred from lightning production by a number of studies. The expectation is that generating more graupel and ice crystals leads to more electrification and thus lightning. Our 2013 paper explored CCN effects in a small latitude thunderstorm. The basic finding was consistent with the invigoration hypothesis in that increasing CCN then increased ice production. But at even higher CCN concentration, it started to reduce the electrification again because of greater mass loading and less rime ice splintering. It was also noted that condensation was increased as higher droplet concentrations reduced the excess supersaturation, but only up to a point. We didn't try to isolate this effect from the microphysical CCN effect, and a couple of recent papers by Fan et al. And Grabowski and Morrison have raised this question of how important this added condensation is for the lightning. So that is the main motivation for revisiting this case, to try to determine how the warm rain condensation effect compares to the traditional invigoration effect. The cloud model used here is COMMAS, which features a fully two-moment bulk microphysics, as well as explicit electrification and lightning parameterizations. Condensation rates are calculated explicitly using a subdivided time step, and our 2013 study tracked the number of remaining CCN, but here we count instead the number of activated CCN and allow regeneration of CCN when droplets evaporate. Here is a quick illustration of the large supersaturation that can develop when droplet number is depleted by the warm rain process. The orange contours in panel A show the supersaturation increasing because the low droplet concentration has a reduced condensation rate. Increasing the CCN, and thus the droplet number, fills in that missing condensation. This effect would not be seen if a saturation adjustment procedure had been imposed. So in order to gauge the effect of only boosting the condensation, we took the old setup and first reran a set of control simulations. Then we apply a few different methods to reduce supersaturation while trying to minimize effects on droplet concentration and precipitation development. And here's an animation to show the evolution for 4 background CCN concentrations. CCN 100 is the first to develop precipitation and have echo at the surface. That's followed by 250 and then 500. The 1000 CCN shows the first lightning flash and then later has precipitation reaching the ground. The lightning production for these 4 simulations is shown here in time-height format. It's obvious that the lightning changes dramatically as the microphysics respond to higher aerosol content. For these, there is a monotonic increase in total flashes from 4 to 265, but that may not happen in other cases. So what are the main microphysical changes? These time-height plots show the layer masses of cloud droplets in gray fill, rain in red contours, and graupel in blue contours. As the CCN increases, more droplet mass is retained, rain mass develops later and more slowly, and graupel mass increases. The collision coalescence process becomes less important, and the riming growth becomes more dominant. Now we have time-height maximum simulated radar reflectivity. Delayed precipitation development is notable also in the first appearance of reflectivity at later times and higher altitudes, as noted by the blue arrows. Between 100 and 1000, there's a delayed echo at the ground by about 10 minutes. For total condensation, we see an increase as CCN goes from 50 to about 500, and not much change above that. With the added latent heating, there's a corresponding increase in updraft volume, although other factors are also playing a role here. Alright, so how do we try to force condensation at the lower CCN values? Single moment bulk schemes generally just apply a saturation adjustment to eliminate supersaturation. So the first experiment is then to apply a tight saturation adjustment to reduce SSW to about 0.1%. With a two-moment droplet category, however, we have to consider effects on droplet size. And it turned out that adding only mass would cause a dramatic acceleration of the warm rain process at low CCN. So we ended up adding the condensation mass as droplets of the current size, which still affects the warm rain process by increasing the droplet concentration, as we'll see shortly. If we only adjust the saturation down to 2%, however, there is less effect on rain production, so mass can be added with almost no extra number. A 1% limit seems to have similar results. A third option is based on the fan et al. Method and creates a reserve of small ultrafine aerosols that only activate when supersaturation exceeds 2%. And the fourth option uses the power law aerosol size spectrum C times SS to the K. This allows additional CCN to continue to activate when supersaturation exceeds previous values experienced by the parcel. So here's the spoiler plot for what happens with lightning for these different options. This first plot is the total number of flashes from each simulation. First note the substantial increase in lightning flashes at low CCN of 50 to 500, especially for the 0.1% supersaturation and the ultrafine aerosols. In all cases, however, we see a dramatic increase at higher CCN. The 0.1% case has a maximum number of flashes at 500 CCN, but total flashes does not account for flash size and other factors. So instead we can look at the total charge transferred by lightning, and here we get very similar trends for all experiments. The 0.1% and CSS to the K options start to trend upward at lower CCN because they tend to boost the droplet concentration as noted earlier. Thus they act as effectively higher CCN values. And now let's look at some details about what is going on in the different cases. Here is a quick comparison of the lightning flashes for the 100 CCN case. As we just noted, the 0.1% saturation adjustment and the ultrafine aerosol have the largest effect on lightning. The 2% adjustment has the least impact, only 3 extra flashes. On a quick aside, here's the total rainfall for all the cases. All but one has a maximum rainfall around 250 to 500 CCN. The 0.1% adjustment has an anomalous trend with a maximum at the lowest CCN of 50, but it's not really clear yet what that indicates, and we'll need to explore that further. Let's now look at what happens to the total condensation. Here's a comparison of the control and the 0.1% adjustment, where we can see that the adjustment really maximizes the condensation up to the levels of the control at high CCN. The updraft volume is also substantially increased by the adjustment. And now looking at the 2% adjustment, we see a consistent but smaller increase in both condensation and updraft volumes, and there is not much effect at all at CCN of 500 and higher. If we now integrate the condensation over the whole storm lifetime, the 0.1% adjustment stands out at low CCN. The ultrafine and 2% adjustment seem to converge at about 500 CCN and higher. For total deposition on the right, there is just as much increase with CCN as for condensation, and in both cases, The values basically converge at high CCN. Invigoration is often couched in terms of the peak updraft. As we can see here in this plot, the peak updraft can be a bit noisy, and it does not necessarily correlate well to lightning or the total condensation. It can be useful, but it's not really the best measure of storm energetics. So let's look at some integrated energy quantities. Here we see the space and time integrated updraft kinetic energy on the left, and the gravitational energy of precipitation on the right. The kinetic energy shows a monotonic trend up to 500 CCN and then basically levels off. The gravitational energy continues an upward trend even at high CCN. One factor here is probably that graupel density decreases at high CCN, which causes slower fall speeds and thus a longer residence time of the graupel. And as you can see here on the right, the time-integrated graupel mass plots have a very similar shape as the gravitational energy. But the lightning total channel length on the left has a sharp increase between 500 and 1000, like we saw with the other lightning parameters. And we don't see that in the graupel mass or the energy plots. Total Riemann growth, on the other hand, has a somewhat steeper transition, but ice multiplication has an even more dramatic increase from 250 to 1000. This isn't too surprising, since ice-ice collisions are the driving process of electrification. So the final word is that increasing the total condensation at lower CCN can boost lightning, but only to the extent that it can increase the production of graupel and cloud ice. So our conclusion is that the warm phase invigoration plays a role in favoring greater electrification, but it is still the microphysical process effects that are the most important in transitioning from warm rain to cold rain processes and play the main role in lightning production. Although we've only shown one case here, we've also had similar results using bin microphysics and also using a second weak shear sounding. And please be sure to check out the talk by Jessica Blair with preliminary results on CCN sensitivity in a supercell storm. Thank you, and see you at question time.